I've been working on the research for cumene process for so long and I still couldn't get it. Yay! Why is this so complicated? I wish someone could just explain to me step by step. Huh? Ooh, crazy!
Greetings, I am the genie of knowledge. I have one wish that I can grant for you.
I wish to understand cumene production for my research.
I can't really just put anything knowledge into your brain, but I have 3 engineers that can help you understand it.
Hello, I heard you wish to understand the cumene process.
Yes, the process is so complex and I can't seem to understand it.
Don't worry, let me explain to you.
Now, let me explain how cumene is produced in an industrial chemical plant. So first of all, cumene, also known as isopropyl benzene, is produced through the alkylation reaction between benzene and propylene. So the process begins when fresh benzene and also fresh propylene enter the system. So some of the benzene from the separation section is also recycled and mixed with the fresh feed. So this recycle helps to maintain a high benzene to propylene ratio, which improves selectivity toward cumene and also reduce the unwanted byproduct. So all of the streams are first combined in a mixer to form a uniform mixture. So the mixture when passes through a heat exchanger where it is preheated before entering the reactor. So next, the heated system enters the alkylation reaction. So inside the reactor, the benzene reacts with propylene in the presence of catalyst to produce cumene. So the main reaction is benzene will react with the propylene to produce cumene. So a small side reaction can also occur where cumene reacts further with propylene to form diisoprosyl benzene, or also known as DIPB. So after the reaction, the mixture goes through the several distillation columns for separation. So first, the propane column removes light components like propane. Then the benzene column separates unreacted benzene, which is recycled back to the process. And then the cumene column separated high purity cumene in the main product. And the heavier bottom stream, mainly containing DIPB, is sent to a transalkylation reactor. So here, the IPB reacts with benzene to produce more cumene, which increases the overall yield. So finally, the products from the reactor return to the separation section so the newly formed cumene can be recovered. So overall, the cumene production process combines reaction, separation, and recycling to maximize product yield and minimize waste.
Oh, I see now. I kinda understand about this whole cumene process, but how do engineers know how much material is entering and leaving the system?
That's where principle of chemical engineering comes in, especially mass balance and energy balance.
So, let me explain the mass balance and energy balance in cumene production. We will look into the non-reactive reaction, specifically on propane distillation column. So, to find the mass balance, we assume that the recovery at the overheat is 99% from the feed. The molar flow rate of the feed containing propane, benzene, DIPB, and cumene is 600 kmol per hour. To begin, we need to calculate the DOF where there is 6 unknown, and by identifying 6 independent reactions, we can conclude that the DOF is 0, which means the reaction is solvable. Then by substituting every value that we have in this equation, we will find the value for every component unknown in this reaction. Next, for the reactive reaction, we will look into the alkylation process. First of all, we need to come up with the chemical equation that happened in this reaction. Then we need to identify the conversion rate. So in this case, propane conversion is 100%, cumene selectivity is 90%, both propane and the IPB is 5% selectivity. By using this stoichiometric ratio, we can solve the generated mole for cumene, propane, and the IPB, also consume mole for benzene, and also the mass flow rate for every component in this reaction. To proceed with energy balance, we need to find the mass balance first. So, for both reactive reaction and non-reactive reaction, we need to set assumption for reference point to find the heat generated. In this reaction, we can neglect the work done, kinetic energy, and also potential energy. Hence, by using the general energy balance formula, we could get that heat is actually equal to the change in enthalpy. The change in enthalpy is obtained when the total enthalpy out is subtracted with total enthalpy in. Total enthalpy for each component can be obtained using the integral of Cp value or also by referring to the enthalpy table. So in this reaction, we can conclude that the heat generated in this propane distillation column is 90,806,177 kg per hour. For reactive reaction, energy balance formula has additional formula where enthalpy in and out is needed to add with the product of the extent of reaction and change in heat of formation for product and reactant. By using the same way to find the enthalpy, we need to calculate every component in this reaction. Since we have two equations in this reaction, the product of the extent of reaction and change in heat of formation need to be totaled up and add to the change of enthalpy for product and reactant of this reaction. Lastly, the heat generated obtained in alkylation reaction is 2,406,250 kJ per hour.
That makes so much sense. But all these chemicals flowing through pipes and equipment, how do they control that?
Excellent question. That's where fluid mechanics become important. So, in this table, we have identified the flow rate, diameter, length, temperature, and pressure for each stream. However, the pressure drop needs to be calculated. We also included the material according to the scale 40, type of fittings, and its justification. From the known viscosity of each fluid, by using the formula, viscosity of the mixture equal to the total mole fraction of component multiplied with viscosity of component, we get this table. So for stream 1 until 17, except for stream 7, 9 and also 12, is a stream contains a liquid mixture. Thus, to find the density of the liquid mixture, we must find the mass fraction for each component of the liquid mixture using the mass fraction formula. From there, we can calculate the density of the liquid using this formula. But for the stream 7, 9 and 12, its component consists of vapor. Thus, we assume that the gas behave ideally. Hence, using the ideal gas law formula, we can obtain the density for each stream. To find volumetric flow rate, by using the known value of molecular weight for each substance and formula Q equal to m over rho, we obtain the following value. And we can calculate the velocity. Replace all the value obtained earlier inside this equation to calculate Reynolds number. Reynolds number can be used to identify the characteristic of the flow, which is turbulent in this case. Then we can find the friction factor, and finally we will obtain the pressure drop by using this formula.
First, we estimate the pump power required to deliver the main product to storage. Energy losses in the piping system are calculated using Reynolds number, friction factor, and friction loss equations. These values are then applied in the Bernoulli equation to determine the pump work. Several assumptions are made: steady flow rate, negligible velocity change, and pump efficiency of 80%. Based on the calculations, the Reynolds number indicates turbulent flow, and the final pump required is approximately 116 watts. Next, the cumene product leaves the distillation columns as the overhead stream, where it is separated from a heavier component such as diisopropyl benzene. The vapor cumene is condensed into liquid before being transported. The liquid cumene then passes through a centrifugal pump to provide sufficient pressure to transfer to the storage facility. A check valve prevents backflow, while a control valve regulates flow and pressure. The piping system uses K40 carbon steel pipes, which are commonly used in petrochemical plants due to their mechanical strength. Since cumene is flammable, storage tanks are installed above ground with bund walls and proper safety equipment. With a production rate of 370.9 meter cubic per day, a 400 meter cube storage tank is selected to ensure safe storage capacity. The tank storage is designed with a safety margin, maintaining a pressure at least 2 atmospheres above normal operating pressure. The temperature is kept above 35 degrees Celsius for an additional safety margin. The tank is vertical cylindrical type with a fixed cone roof, ideal for storing aromatic hydrocarbon like cumene. It has a height of 8 meters and outer diameter of 8.016 meters with a shell thickness of about 8 to 9 millimeters. Made from carbon steel A36, it's cost-effective and compatible with cumene. The production rate is about 380 cubic meters per day, and the tank volume is approximately 413 cubic meters.
In conclusion, a strong understanding of chemical engineering principle and fluid mechanics is essential in designing a cumene production process to ensure efficiency and safe operation. Mass balance and energy balance are important for determining the correct flow rates, composition, and heat requirement of each unit in the process. Fluid mechanics is also crucial for designing the piping and pumping system that handle fluid flow throughout the plant. By applying concepts such as Bernoulli equation and pressure drop analysis, engineers can control fluid flow, account for friction losses, and ensure stable and reliable operation. Overall, integrating chemical engineering principle with fluid mechanics allow theoretical concepts to be applied to real industrial process, leading to efficient design and improved plant process.